Good morning, good afternoon, good evening, everyone, wherever you are. Okay, welcome to the fourth webinar series of the University College of Water, Science and Engineering. We are glad to have Xia Wu as our noted speaker for this webinar series. My name is Camila Saya Rebecca, and I'll be your moderator for this series. Thank you. Please, can you hear me?
Yes, Kamla, we can hear you.
Okay. Xia Wu is a postdoctoral researcher at the College of Hydrology and Water Resources, Hohai University in China. She obtained her bachelor's and master's degree from the same college of the Hohai University and a PhD degree from the School of Civil and Environmental Engineering at the University of New South Wales in Australia. Her research focuses on developing the algorithm for parameter estimating and uncertainty quantification in water environment modeling. Her recent achievement is the development of a novel algorithm, the Bayesian error analysis with reordering method, which enables the highly efficient and effective identification of data error sequence during the model parameter optimization. Welcome, Xia Wu.
Okay, thanks. Thanks, Camila. Thanks for your introduction.
Okay.
So can we start now? Start my
Yes.
presentation? Okay. Okay, can you see my slide?
Yes, please, can see.
Okay, I will start. Hello, everyone. I'm glad to have this opportunity to introduce my research. I'm Xia Wu from Hohai University in China. My research focuses on the model calibration and uncertainty quantification. Today, I would like to introduce how to incorporate the data uncertainty in the calibration of the water quality and hydrological models. So my talk contains two parts. The first part, I just introduced the algorithm we developed, which called the Bayesian error analysis with reordering, which can identify the data errors in the model calibration. And the second part, we would like to introduce how to set the likelihood function to get the model parameter we want. It's the skew technique. So let's start from the first part, Bayer method. So for engineering, our work is to build a model to simulate the dynamics of the real world. And we should calibrate the model parameters based on the minimize the residual error between the simulated output and observed output. This approach is widely used and it seems reasonable, but this approach based on several assumptions, we often ignore this assumption. First, we think the model structures is perfect, but most of the model parameters has no physical meaning, so we usually incorporate the model structure errors into the model parameter errors. And another assumption is that we think the observed input and the observed output is perfect, but the data error in the input and output cannot be avoided. Take the hydrological model, for example. The input we usually set as rainfall. We usually consider the average values of the several stations, think it's the catchment rainfall. So it cannot perfect to represent the catchment rainfall. And the output data, we usually use the stream flow data. We get the stream flow data from the rating curve. So the estimate stream flow data from rating curve is not perfect as the observations of the stream flow. So it will introduce the output data error. So the data error cannot be avoided, and it will lead to the bias of the parameter estimation. We build a synthetic case to show how it happened. So for this synthetic case, the green line is the true value of the model parameters, and we end the output data error into the perfect model simulations. We assume the output data error follows the normal distribution with the mean at the 0 and with the variance increase from 0.5 to the 10. So when the output data error, the variance increased, the bias of the parameter estimation will be increased, even when the mean of the random errors equal to 0. So the unbiased random data error will also lead to the bias of the parameter estimation. And this problem often ignored in our real model calibration. So we think if we can remove the impact of the data error to identify the data error during the model calibration, and we can get the more accurate estimation of the model parameters. So this is motivation of our research. So how should we do? Luckily, we cannot identify the time series of the data error in the model calibration directly, but we can estimate the PDF of these data errors. PDF is the probability distribution function. Take the stream flow, for example. We know the actual observation of the stream flow, and we know the estimated stream flow from the rating curve. Compare these two data of stream flow, and we can get the errors of the stream flow data, and we can calculate the PDF of the data error, get this probability distribution, and we can call this distribution as a prior distribution because it just comes from the data itself. It's independent from the model simulation and calibration. It's the statistics of the data itself. So how should we make full use of this prior distribution to identify the temporal changes of the data error? For the current method, we just sampled the error from this prior distribution, and we got one estimation of sampled errors, and we use these sampled errors to correct the data and get the corrected data, and we use this corrected data, recalibrated the model parameters, and get the objective functions. And we can sample them again and again and choose optimal sampled errors based on the minimized objective function. Because when the objective function is minimized, it means the residual error, the difference between the simulations and the observations, will reduce to the smallest value, and it will remove the impact of the data error. So just through the rendering sample to get one sequence of the data error, which is the same as the true data error, it's not efficient and it's not effective. So we think, can we use more information to re-audit this error, to push all this error more close to the true data errors? So we just developed this method, Bayesian error analysis with reordering strategy, to use the reordering strategy to improve the data error efficiency and effectiveness. How it works. First, we should estimate the data error rank, and we should find some information from the total errors, the residual errors. It's the difference between the simulated output and the observed output to find which part of this information is corresponding to the data error. And the residual error can be divided into the two parts. One part is the correlated part. It usually comes from the model structure error, and we can use the first order of the autoregressive model to represent this part. Remove the correlated part, the rest is independent part. It usually comes from the data error. And we can use the rank of the independent part to estimate the rank of the data error. Let's see the result. Here, we also build a synthetic case to see the ability of the different methods to identify the input error and minimize the objective functions. And T method is a traditional method without consider the input error. So the result is worse because it's the result of MSE. The smaller, the better. So for the traditional method, it's worst. And for the D method, we just randomly sampled the errors from the prior distribution and choose optimal error according to the minimized objective function, so it can become better. And with the reordering method, we can see the result can become much better. And when use AR1 model to remove the correlated part and use the independent part to identify the data error, it becomes the best. So the AR1 model can represent the correlated part in the residual error, and the independent part can improve the identification of the data error. And for the data errors, we should distinguish this data error mainly comes from the output data and or input data. If it mainly comes from the output data error is dominant, we can directly use the rank of the independent part as the rank of the output data error rank. If the input data error is dominant, so we should do some treatment because there is a nonlinear transformation from the input to the output, which means we got the bigger output error. It doesn't mean it corresponds to the bigger input data error. There is a nonlinear transformation from the input to the output. How to address this? Let's see the method. First, we should consider the delayed response from the input to the output. It usually comes in the hydrological field. When at the first 10 steps, the rainfall happens and the discharge will not increase immediately. It will happen at the later 10 steps. So we should identify the lag time between the input and the output. Here we develop an algorithm to decompose the simulated hydrograph to identify this lag time. This is how to calculate the lag time. First, we calculate the hydrograph of the 3 days precipitation, and we calculate the hydrograph of the 2 days precipitation. The first day precipitation set to 0, and use the hydrograph of 3 days precipitation minus the hydrograph of 2 days, and we can get the hydrograph corresponding to the first day's precipitation, and to identify the delay between the input to the first positive discharge, and we can identify the lag time for each input data. Here I want to explain more why we don't use the precipitation of the first day to calculate the hydrograph directly and to identify the lag time, because we use the precipitation of the first day precipitation, the hydrograph will have the impact of the basic flow. So all the values in the hydrograph will be the positive. It's hard to identify the lag time according to the first positive. And use this method, 3 days minus 2 days equal to the 1 day, it can remove the impact of the basic flow and easily to identify the lag time between the input to the output. And let's see the result. Here we also build a synthetic case to set the true lag time between the input and output equal to 1, 2, 3. And we use our method, calculate method, which can get the result, which is similar to the we directly set the true lag time in the error identification. So it means this method can automatically identify the true lag time and consider the lag time in the error identification. It can improve the accuracy of the result. I think consider the lag time between input and output can not only applied in the error identification and also can use to other applications. And another part is how to address the nonlinear model transformation from input to output. Here we just developed the second method to deal with this problem. The second method is iterative approximation to identify the root of an equation. Here, the root is optimal error rank. K is stand for the error rank, and the equation is the residual error equal to 0. It means minimize the objective function. So let's see how it works. First, we randomly sampled the errors from the priori distribution. Here, the blue line and the green line is the sampled errors. So we can see through the randomly sampled, it's difficult to match the value at the different time steps with the true input error. We got the input error and we can get the input error rank, and we can use this input error, correct the input data, and recalibrate the model parameter to get the model residual errors. And according to the error rank and model residual errors, and we can use this equation to update the error rank. So let's see. Use this equation to update the error rank at the first time steps. The result is 5.8. So it's not the real rank. So we can rank the rank to get the real rank, get the integer rank. And according to the new rank, we can do the reordering strategy. Here, the first time step, the rank is 6. So we can find the rank 6 error is this value, and we can put this value into the first time steps and to finish the reordering strategy. Here we got a new input error series just with one reordering. We can see the yellow one after reordering, it's closer to the true input errors. So it works. Let's see the result in the real case. In this case, we just built a hydrological model for a catchment, and this catchment has 10 stations of the rainfall data, and we calibrate the model based on the rainfall data from 10 stations separately, and also use the average value of the 10 stations. And we compared the 3 methods, random sampled with reordering sampled, and the reordering sampled first remove the correlated part. So we can see the result. When we use the reordering strategy, it can further minimize the residual error to reduce the RMSE between the simulation and the observation. But there is no big difference between the method, whether we use the AR1 model probably because the impact of the model structure errors. But for the estimation of the input errors, the pink one, we applied the AR1 model. It is more closer to the true value. The green line is the true value. So we can get a more accurate estimation of the input error, just remove the correlated part in the residual errors. Okay, let's do a summary for the Bayer method. First, I just emphasize that we should consider the impact of the data error in the model calibration. And I introduced the reordering strategy to deal with these problems. I would like to talk more about the reordering strategy because we don't directly estimate the error values. We estimate the error ranks. Because for the error values, it's continuous, so it has the infinite combination for the estimation. But for the error rank, it's discrete and it's integer. So estimate the error rank is more efficient than estimate the error value directly. And then we should overcome some problems to estimate the error rank. We should deal with the persistence in the residual error and delayed response, and how to identify the nonlinear model transformation. The more details of the algorithm can be found in these papers. And then we developed this method, the Bayer method, to identify the multiple source of the data errors, to identify the input data error and output data error at the same time. More details could be found in these papers. In these papers, we just to find the prior information of the data error distribution is very important for the error identification, and we should choose the proper logic to identify the interaction in the multiple data errors. Okay, it's all about the first part, how to identify the data error in the model calibration. Let's move to the next part. It's about the skills, how to set the likelihood function to get the parameters we want. In the Bayesian framework, we usually calculate the likelihood function to transfer the prior distribution to the posterior distribution. So for the likelihood function calculation, we usually assume the residual error follow normal distribution, and we can use this equation to calculate the probability of the residual errors. If the assumption that the residual errors follow normal distribution is correct, so the error should be the homozygosity. It means for the different values of the observation, the variance of the error could be the consistent. But in the water resource field, especially in the hydrology field, when the observation become bigger and the errors will become also bigger, so the errors will show the heteroscedasticity problems. Usually we use the data transformation to deal with this problem. And this is the widely used data transformation, but a few studies carry out the systematic comparison of the different data transformation and tell us how to select the proper data transformation. So here in our study, first we just summarized the likelihood function for the different data transformation. It should be noticed for the likelihood function, we not only to change the value of the output observation and output simulation into the data after the data transformation, we also ending this part. This part is the derivative of the observation, model observation, output observation respected to the data transformation function. So we modified the likelihood function for the different data transformation, and then we tested it in this model. This model is a water quality model. And the input is a stream flow, and the output is the concentration of the TSS. It's the sediment in the rivers. So this water quality model just shows how the TSS changes with the stream flow. And we should calibrate the 5 parameters in this model, and we test it in the full catchment in the USA to get the genetic conclusions, and select several performance measures to analyze the ability of the data transformation. So let's see the result. So the first result is about the ability to address the errors heteroscedasticity. It's the main task of the data transformation. Here we choose the metric as Philippine statistics. It can represent the errors normality. So if this metric is close to the 1, it means the errors follow the normal distribution. And we can set the lambda 1. The lambda 1 is the parameter in the data transformation. So for the different data transformation, we can set the lambda value. When the lambda value decrease from 1 to 0, and we can see this metric increase from low values to the 1. So it means when the lambda 1 reduce, and the ability of the transformation to address the errors heteroscedasticity will be increased. Why it will happen? Let's analyze this result. This figure can show how data transformation works. The blue line is our original values, and the black line is data after data transformation. So we can see for the low values, the data before data transformation is smaller than the values after data transformation. But for the high values, the values before data transformation is bigger than the values after data transformation. So the data transformation just expand the value of the low points and reduced the value of the high points. So it just balances the errors between the low values and high values. When the lambda 1 became smaller, and this ability will become stronger. So the lambda just increase the impact of the low values in the calibration, and reduce the impact of the high values in the model calibration. So we can check the result in these figures. We choose the RSR to measure the goodness of fit for the difference between the observation and the simulations. When RSR is 0, it means the best fit. And we calculate the RSR for the all values, high values, and the low values. So we can see with the smaller lambda 1, the RSR for the high values become bigger. It means the fit become worse. And for the low values, the RSR become lower. It means the fit become better. So smaller lambda 1 will lead to the worse fit for the high value and better fit for the low values. It's just supported this finding. It will do some balance between the low values fit and high values fit. So it's a key finding in our study. If we want to do some analysis for the peak simulations, for example, the peak flood, so we can set the lambda 1 bigger in our research to get the better simulations to fit the peak values. And if we want to analysis for the low values, such as the drought analysis, and we can set the smaller lambda 1 to get the better fit for the lower simulations. Okay, it's the summary for the second part. We can find the more details in this paper. So in this part, I just introduced we should set the proper likelihood function according to our research requirement. Just apply the data transformation. So in this study, we just find the lambda 1, the value of alignment, played an important part in the performance metrics. And this is the summary of the impact on the performance of metrics with reducing the lambda 1. And none of the data transformation provides the best performance across all metrics. So here we set a flowchart of selecting data transformation according to our research requirement. Okay, it's all about my research for these two parts. And this is my contact information. Thanks for your listening, and any question. Oh, okay, I finished.
Okay, thank you so much for this insightful presentation.
Thanks.
Please, if you have any question, you can ask. You can ask your question.
Yeah, it's more technique, so it's complicated. Yeah, it's just an algorithm development. So we want to expand this algorithm into the more applications. It just provides a clue to how to incorporate data uncertainty into the model calibration to balance the uncertainty between the data and the parameter. You mean the Bayer method? We just try this method to analysis in the flood simulations. It can improve the parameter estimation for the flood modeling, but for the drought modeling, we not test it, so it's quite questionable. But for the flood, it can better to catch the peak simulation when we consider the data uncertainty.
Yes, please, can I come, please? I have two questions.
Sure.
Yes, please, you can ask.
Yes, thank you. And my first question, I didn't understand, like, what do you mean by true error? The term of true error, what do you mean by that? And,
yeah.
Yes, the second question, like, if I have the missing data in my data sets and I fool it, so is it a error, a true error, or what's kind of error is it? Thank you.
Okay, the true error, actually we didn't know the value of the true error. Is the true error just mean the exactly the errors between the observations and the true data. So it's the meaning of the true errors, but the in fact we didn't know the true errors. We just want to close to the true values, true errors. Sorry, I cannot understand the second question. So you have the missing data and how
Yeah,
to
yes,
how
the
to know.
missing data, and you use another method to fold the missing data. Is it? I can consider this the like a error, or what kind of error data?
Actually, if you have the missing data and you can put some guess into the data series, and this method can help you to get the more accurate estimate of the data. So you just guess one value to make this series full, and this method can help you to get the more accurate data, consider the data error.
Okay, thank you.
Okay, any question? Yeah, it's just about algorithm, but it's there is several genetic ideas in my study. First, we should consider the delayed response, delayed lag time between the response and the predictor. So in other prediction, we should also consider the delay between the input and output. It can improve the prediction accuracy. And also we should consider the correlated part in the residual errors. To remove the correlated part, we can get the more accurate information for the data errors.
Please, any other question?
Probably we can discuss after this seminar, because maybe it's I'm not explain it clearly. And if you just want to use our method to other application, I can provide the code for you and write some code for your research, so we can discuss after this seminar.
Okay, so please, if you have any other question or anything you want more clarification on, you can reach out to her on her email.
Yes. Yes. Yes.